Hi, this is a second video on rational functions and graphs of them. In the last video we talked about horizontal and vertical asymptotes. In this video we'll expand upon asymptotes as well, horizontal, vertical if there are any, and we'll also talk about holes in functions, holes in graphs of functions, and the slant or oblique asymptotes. So for this function here we have the function f of x equals x squared minus 4 divided by x squared minus 2x minus 8. This one here is going to have both horizontal and vertical asymptotes, and it's also going to have a hole in the graph. So let's look at our horizontal asymptote first. First off, we'll notice that the degrees of both the numerator and the denominator are the same. So that tells us that the horizontal asymptote is going to be the ratio of their leading coefficients. So our horizontal asymptote is going to be at f of x equals coefficient of x squared is 1, coefficient of x squared is 1, so 1 divided by 1 is 1. So that's where our horizontal asymptote is. And we could graph that over here. There's our horizontal asymptote. Now our vertical asymptote. Alright, in order to find where our vertical asymptote is, we need to simplify the numerator and the denominator. And in the process, we're going to find a hole. So if we look at x squared minus 4 over x squared minus 2x minus 8, we could factor both the numerator and the denominator. The numerator is a difference of squares. So that'll be x plus 2 times x minus 2. And in the denominator, this here is going to be x minus 2, or x plus 2, times x minus 4. The numerator and the denominator have a common factor of x plus 2. So they're going to simplify out. And that's going to leave us with a hole at x equals negative 2. Basically set x plus 2 equal to 0, and our hole is going to be at x equals negative 2. So we'll have a hole at x plus 2 equals 0, or x equals negative 2. That's where our hole is going to be. And then our vertical asymptote is going to be when x minus 4 equals 0. So our vertical asymptote is going to be at x equals positive 4. So positive 4 is over here. There's that right there, and I'm actually going to extend my x-axis in this direction a little bit further. Okay? So now we have our horizontal asymptote, our vertical asymptote, and where our hole is in the graph. Let's find some points and let's plot them. Okay? And to do so, we'll do an xy axis, an xy chart here. We'll do an xy table of values. Remember, this function here is going to behave the exact same way. It's going to behave the exact same way as f of x equals x minus 2 over x minus 4. Okay? It's going to behave the exact same way because there's a common x plus 2 factor. Okay? So let's look first at, let's say x equals 3. So when x equals positive 3, our value of y is negative 1. So it's going to be right here. What about x equals 2? That's going to give us a value of 0. At x equals 1, That'll give us 1/3. Right about there. When x equals -1, or 0 we could say, x equals 1/2, and x equals -1, we get 0.6. So the 1/3, that could be 0.3. 1/2 is 0.5. We get 0.6. And now when x equals -2, we have a hole in the graph. Alright, so we represent it by a hole. And it looks like this graph, as we go towards -infinity, it's going to approach this asymptote. Alright, and as we approach the x value of 4, it looks like it's going to approach this asymptote here. So this half of the graph is going to look just like that. Okay? And we have a hole at x equals -2, so we leave it as a hole. And now if we look at this part of the graph, let's say x equals 5, y equals 3, or f of x equals 3, that's 6, y equals 2, or I should say f of x here, that's 7, that's going to be about 1.7, and at 8, it's going to be about 1.5. So if we graph all these points here, x is 5, it's going to be 3, right there. Yeah, at 6 it's 2, 7 it's going to be 1.7. So you can see this graph is sort of trending downward. It starts way up top here, and it passes through these points here, and it approaches this horizontal asymptote. And again, here is where our hole is. Our hole is at x equals -2. That's not a part of the graph. When you put -2 in, this function is going to come up as undefined. Alright, so that's an example where it has both a horizontal and vertical asymptote, but it also has a hole. So it's important to know when holes occur in graphs as well. Right, so last example for graphs of rational functions here. We have the function f of x equals x squared plus x minus 3 divided by x plus 2. Let's start off by finding a domain restriction, especially with the denominator. We'll find our vertical asymptote. Okay, so for our vertical asymptote, that's going to be whatever value x is that makes the denominator 0, and that's going to be -2. So our vertical asymptote is at x equals -2. And we could graph that in our xy axis right there. And then we need to find a horizontal asymptote, or another asymptote. What you should notice here is the degree of the numerator is 1 higher than the degree of the denominator. The degree of the numerator is 2, degree of the denominator is 1. So that tells us we're going to have something called an oblique or a slant asymptote. And that oblique or slant asymptote, we find it using polynomial division. In this case, we're going to use synthetic division and divide using that method. So if we use synthetic division here, we have the opposite of 2 outside, and then we take the coefficients, 1, 1, and negative 3. Alright? I don't care, in this case, what the remainder is. All I care about are these values right here. So if we drop this 1 down, we get a 1. Negative 2 times 1 is negative 2. 1 plus negative 2 is negative 1. Negative 2 times negative 1 is positive 2. Negative 3 plus 2 is negative 1. As I said, I only really care about those two values here. And that tells us when we divide x squared plus x minus 3 by x plus 2, we're going to get x minus 1 plus a remainder of negative 1 over x plus 2. This right here, this value right here, is what I care about. That line right there, if we are to graph it, is going to be the oblique asymptote. So our oblique asymptote is that f of x equals x minus 1. And remember, f of x is just a fancier way of saying y equals. So it really is y equals x minus 1. So, and we could graph that as well. That's going to be right here. There's our oblique or our slant asymptote. There will be no horizontal asymptote. There will only be a vertical asymptote and an oblique asymptote. So now that we found our oblique or slant asymptote and our vertical asymptote, let's go ahead and graph this function here. And what we'll do is we'll use a table of values here. Alright? Let's look at values of x that are less than the value of our vertical asymptote, negative 2. So like negative 3, negative 4, and negative 5. When we look at those values, when we evaluate this function f of x at x equals negative 3, we get a y value of negative 3, or an f of x value at negative 3. When x is negative 4, we get an f of x value of negative 4.5. And when x is negative 5, we get an f of x value of negative 5.7 about. Negative 5.6 repeating. So if we graph those, okay, negative 3 is right here. Negative 4, negative 4.5 is right about here. And negative 5, negative 5.7 is right about here. So it looks like this graph here is going to approach this oblique asymptote here. And then to find out what our behavior is after this point here, we need to pick a point such as negative 2.5 for x, something in the interval between negative 3 and negative 2, and see what happens. Well, if we evaluate this function f of x at negative 2.5, we get a y value of about negative 1.5. So at negative 2.5, the value is right about here. We could further look at this graph here, look at the function here, and evaluate it at negative 2.25 to negative 2.25 to see what happens after this point if it keeps coming up towards this vertical asymptote as well. And what we realize is if we evaluate the function f at negative 2.25, we'll get an f of x value of about 0.75. So that's going to be right about there. So this graph, it's pretty much laying on this oblique asymptote, and then it curves up and it starts hugging this vertical asymptote. Like that. Okay? Now we have this part of the graph. Let's look at the other half of the graph. Let's look at points that have x values greater than -2. So let's pick -1, 0, and +1. So when x is -1, our f of x value is going to be -3. When x is 0, f of x is -1.5. And when x is 1, our f of x value is 0.3 repeating, or 1/3. So let's graph those 3 points there. We have -1, -3. -1, -3 is right here. 0, -1.5 is here. 1, 0.3 is right there. So it looks like this graph is going to keep going this way and hugging this oblique asymptote here. We'll just keep coming and coming and coming, just like that. And now we need to analyze what happens here. Does it come back out this way? Does it come this way? Does it magically come up? Well, we know it's not going to come up because we can never get a y value, an f of x value, that lies on that line there. So what we need to do is what we did over here. We need to pick values in the interval from -2 to -1. So let's pick -1, -1.5, and -1.75. And when we pick those points, those values of x, -1.5, we get -4.5 for f of x, and when x is -1.75, we get -6.75. If we graph that, -1.5, -4.5 is right here. And then -1.75, -6.75 is right about here. So this graph, after it comes up, climbs this vertical asymptote, it starts to climb on this side of the vertical asymptote and rises and hugs the oblique asymptote. Okay? And that right there is what the graph looks like. And from here, we could state our domain and our range of the function. The domain, well, domain restrictions, there's two things that you need to consider with the domain. Can't ever divide by 0, and you can't create an imaginary or complex number, or have a negative under a square root, or under an even root, I should say. So our domain values, in this case, we don't have to worry about creating imaginary complex numbers. We just have to worry about when the denominator is 0. And that's only going to happen when x is -2, as we said in our vertical asymptote. So our domain is all real numbers, but the restriction is x cannot be -2. Our range, well, look, we can get any value of f of x or y. I should say this is also y, right? Okay. We could get any value of y that's close to -infinity. We can produce any value of y up to +infinity. So our range here, we can get any value if we input any value for x, right, except for -2, right, we will get any real number value for y. So our range here is all real numbers. can certainly discuss the end behavior of this graph. End behavior as x goes to negative infinity or gets infinitely smaller, f of x, or the value of y, gets infinitely smaller. And then as x gets infinitely bigger, the value of f of x gets infinitely bigger as well.